You are here because you would like to master the 10-minute guide for writing ionic equations by Airbus Chemistry. I would wanted to create an animation for this video, but unfortunately I didn't have time because of 2025 O levels time constraints. Hence, my apologies, but let's get started and stay tuned. So, for writing ionic equations, here we go. We should first understand the definition of an ionic equation. Because if you know how to write ionic equation in exams fast and direct, it's going to save you a whole lot of time and yet get you the marks. So here we come. Okay, so understand the definition of the ionic equation. So it is so as the word ionic equation suggests, so it involves it shows the ions, right? And these ions are what is happening, right? It is involved in the chemical reaction. So it's basically a deeper depth of understanding into the chemical reaction because you are investigating which ions are the ones that are actually involved, right? During the chemical reaction, right? When the reactants react to go and form the products, then those ions that are not involved, they are called your spectator ions. All right. So I'm going to teach you all some. I'm going to teach you all some special ways to write ionic equations for certain reactions, right? Because what your school will have taught you is that say you'll see. Okay, so these are some ionic equations of what were common reactions, and neutralization is one of them. Okay, so this good old method is what your school will have taught you. Your school will have taught you these three steps, right? So you write out the chemical equation, or sometimes may even have been given to you. Then what you do, you split this up into this whole entire chunk. So you find the aqueous chemical species, right? Then you split this aqueous chemical species, the chunk into this whole entire chunk over here, right? Then over here you find the common spectator ions in. So the spectator ions are basically those that remain the same in the reactors and products because these are the ones that are not involved in the reaction. So right, so what they are going to do is they are going to do this. Okay, so you're going to cancel the NaCl, boom boom boom. Okay, then you end up with this after we simplify the after we simplify the ratio, the mole ratio of the remaining ions and the chemical species left in the ionic equation. Right, now this is the good old way, but now, for a faster way, right, I need you to have a true understanding of the definition, right? So you need to really know which reaction is going on, right? If it's a neutralization, right? So neutralization means what, right? So it's the acid and the base neutralized to form water, right? And this, okay, so this thing, right? So this thing is basically, so the acid, as you remember, right, from the acid base chemistry, your understanding, right, is that acid is when it dissociates, it's going to form it's going to form a lot of H plus, right? A higher concentration of H plus and OH minus. So it's mainly H plus. The base, right? Okay, I was to say alkaline because the base when soluble water is an alkaline, and this alkaline is largely or mainly OH minus, right? Then it neutralizes to form your H2O liquid, right? Now, but this, okay, so this is actually how I got the ionic equation because what is the only thing is involved? It's only an acid, H plus. The base is involved, OH minus, form water, H2O liquid. The rest, which whether the rest of the ions, whatever sort it is, I don't care, right? Now, so but okay, this is only applicable if acid and base are in aqueous state because yeah, and it's soluble in water. Then, if you remember what I taught you just now, when the base is insoluble in water, when base is soluble in water, it's called alkaline, right? Now, but sometimes, right, some bases they are insoluble in water, right? Like for instance, metal oxide, right? Most of the metal oxides, especially CuO, this is insoluble. It's in solid state because it's insoluble in water. So this one, right? Only so this one, this being in solid state. Too bad I cannot produce the OH minus, right? But then the H plus as you can produce from here, right? Then so this is the only one that's there with the spectator, right? The H plus comes from here. So this is the spectator. This is the spectator. But then this one I cannot ignore because this one actually came from the exchange of partner over here, right? So then the water is in liquid state, so I cannot ignore, right? So, but then, and also here is solid state. So this gives me to this ion equation, right? So it's this metal oxide, right, plus 2H plus. Why 2? It's because the number here is actually 2. So this is actually a diabasic acid, right? So 1 mole of sulfuric acid will dissociate completely to give you 2 moles of H plus ions, right? Then after that, then you also see, right? So because this one comes in a solid state, so no choice, I must copy them here, right? Then I also must copy the water here. And the only factor is SO4 2 minus that is not involved in the reaction at all. All right? Okay, now this one acid carbonate reaction, right? So if metal carbonate is soluble in water, right? So this is going to what is going to happen, right? So but again, right? But again, okay, you see this, right? You see this, okay? Acid carbonate, right? Give you salt, carbon dioxide, and water. Usually the salt is the one that is not involved in the reaction. The only one that's involved in the reaction is acid carbonate. That is why you must truly understand the name of the reaction. This reaction is called acid carbonate for a reason. Acid H plus. Metal carbonate CO3 2 minus. Right? So you see, so this is actually how the name is formed. Right? Then you need your carbon dioxide is this one is your gas, so cannot ignore. This one is your liquid, so cannot ignore. So this is actually how it is formed. But again, there is a caveat, right? So this is only applicable for if the metal carbonate is soluble in water. And if you were to recall your solubility table, this is going to be your sodium, potassium, aluminum, sodium, potassium, ammonium carbonates, right? Your SPA salt. That, but if for the rest of the metal carbonates, right, and they are mostly group 2, they are insoluble in water, right? So basically what I did was I basically let M be a metal of +2 charge. So same thing again, right? The MoCO3 is a solid. This is +2, this -2. That's why the ratio is 1:1. When it simplifies, right? Then of course the 2H plus over here, right? So this one is actually coming from MCO3 solid, so I cannot ignore. Then again plus the CO2 plus the H2O liquid. Can? Okay, then let's move on. Okay, so this one, ammonium salt plus alkaline give you salt plus water plus ammonium gas. So now, this one, ammonium salts, right? Now, let's understand the name. Okay, the word salt, right? We don't know what's the anion, but for sure you know, this is NH4 plus. The alkaline, what ion is it? It is mainly OH minus, right? Then salt, you usually ignore, right? So it's good. So very simple. We copy here, right? So this for not forgetting the stick symbols, right? Um, Not forgetting the stick symbols, right? Then this is going. Then so this is going to be H2O liquid plus NH3 gas. Then you check whether it's the equation balance. The answer is yes. So there you go. This is your ionic equation, right? This is your ionic equation. Let me tell you that all the ammonium salts that I know are except for ammonium chloride are soluble. So no, so by right, most of the time it should work. Because most of the time, right, this actually talks about this is actually involving an aqueous ammonium salt and alkaline. Alkaline already tells you it is a base that is soluble in water, so it's in aqueous state for sure. Alright. Okay, then next one. Displacement reactions. Right? And these reactions are redox. And I'm going to talk specifically about metals. Okay? So this one, right? Displacement reactions of metals or which are redox, right? So this one, here we go. Okay, so now in your so first of all, please go and remember your reactivity series. Okay. Now, so because of this, I'm going to share my computer. Um, I'm going to share my computer, and this is the reactivity series. There we go. Okay, so now this is basically the reactivity series. There are 3 indicators for you, right? There are 3 indicators for you: your carbon, your H2, your H plus, right? Um, Okay, so now you should know what they are for. So what you learn is about the reactivity series is this thing called the metallic character. And the metallic character is any metal. Is trying to say that any metal, right? That is what you call above in the reactivity series will be preferentially oxidized, right? Because it readily loses an electron to go and form a cation of stable electronic configuration. Then the less reactive metal is the one that is preferentially reduced, right? That is preferentially reduced. So this is what is happening is actually there's actually a redox reaction going on, right? So if you truly understand what is happening, right? So what I'm going to do, right, is I'm going to write down there it's you can think of it like electrochem. There's an oxidation half equation, there is a reduction half equation, right? So what I'm going to do is I'm going to stop my share and go back to my work, right? So replace displacement reactions, right? So this one is oxo. You can think of it like two half equations, right? So oxidation, more reactive metal, right? Then this one is reduction. This one is your less reactive metal, right? Below in reactivity series. This one is above in reactivity series, right? So this one is going to this one is going to be, let's say, magnesium. So magnesium solid is going to give you Mg2 plus equals how many electrons did you lose along the way? 2, because of the 2 plus charge. Reduction, here we go. Zinc, so let's say you have zinc, right? Zn2 plus equals, right, plus 2e minus, right, it's going to give you Zn solid, right? So you just all need to do is just combine together. So Mg solid plus Zn2 plus equals will give you zinc solid plus Mg2 plus equals. Okay, can this one is easy example, right? Easy example. Easy example because both of them are 2 plus charge. But you have to be careful, right? If let's say one of them are different charges, right? So let's say I was to give you maybe aluminum, right? Let's say I have to give you magnesium. Yeah. Okay, let's say I want to give you calcium and aluminum, right? So aluminum is what I can think of 3 plus charge from the moment. Okay, oh no, let me give you iron. I think iron is better. Okay, so now, but let's say you got iron, right? So again, maybe I got magnesium, right? Let's say I got magnesium oxidized because it's above. Then let's say iron, right? Iron 3 plus. Let's say they give me an original solution of iron 3 plus, right? Then so to reduce to iron solid, it is 3 plus charge. I'm going to have to gain 3 electrons. So in this case, right, what I'll have to do, right, is I will have to ensure that the total number of electrons transferred, total number of electron transferred is the same throughout, i.e., number of electron lost due to oxidation, right, equal at anode, for example, because sometimes can be like that. Okay, when you're doing when you're doing this thing called electrochemical cell. Now, equals to number of electron gain at cathode due to reduction, right? Due to reduction. Okay, oxidation reduction, electron loss, electron gain. There, you see? So now, so if we so what I'm going to do is I'm going to use the find LCM. The LCM of 2 and 3, this is simple mathematics, secondary 1, E-math. So in E-math, you all learn that the second that it is 6, that the LCM of 2 and 3 is 6. So here we go, times 3 to equation number to the oxidation half equation. So this one is going to give us 3mg2 plus equals plus 6e minus this one. Then this one, okay? Here we go. So 2fe3 plus equals, right, is equals to so sorry shit, I forgot the 3 the sorry the 6e minus, right, it's going to give you 2 Fe solid. Then all you do is you combine them together, right? So you are going to combine 3Mg solid plus 2Fe3 plus equals is going to give you 2Fe solid plus 3Mg2 plus equals there. So here you go, right? Or okay, then I also want to teach you something, right? How do you check, right? How do you check whether equation balance, right? How do you check whether equation balance, right? How to check whether equation balance is to compare the charges. So you can see, right, on the left hand side, right, LHS 2Fe3B plus, right, is the one carrying the charge. So it's equals to 2 times plus 3 is equals to plus 6. RHS, right? Because they should be equal charge because the number of electrons transferring throughout remains the same, right? So this is going to be 3 times plus 2 because it's 3mg2 plus, right? Then this is going to be plus 6. So this one correct, and then this one correct because it's the same. So equation is balanced. A special case, right, of the displacement reaction on metal, right? Special case. Okay. Shit, what happened to my pen now? Is it even working? Let me test my pen first. Okay, so special case of redox or similar to metal displacement, right, is your acid plus metal reaction to give you metal salt plus H hydrogen gas. Right, this one. This one I'm pretty sure you know. It's very traditional in your acid-base chapter. So now let me go and share my PowerPoint. Okay, so share PowerPoint. Okay, so as you all can see here, right? You all can see here. So this is the purpose of the H plus indicator, right? Any acid that is above H plus, right? So basically, any acid that is above H plus, right? All the way over here, right? All the way over here, right? Any acid that is above this H plus indicator, right? Can essentially react with dilute acids. Because these metals, right? These metals are essentially oxidized, preferentially oxidized as compared to hydrogen, right? So the H plus in the acid has oxidation state +1. It's going to reduce to 0 oxidation state in hydrogen gas. Then the metal solid has initial oxidation state of +0. When it oxidizes to a metal salt, it's going to form oxidation state corresponding to the charge of the metal cation in the metal salt. Right, so this is actually this is actually a special case of metal displacement for you to understand, right? So this is actually a redox reaction, right? So the acid, here we go, right? So the ionic equation, so this one should be your H plus, right? Your aqueous. Um, then this one, metal. Okay, so your metal can be this one is so let's say I'll say okay, okay, this one should be 2H plus, okay? Because hydrogen gas here is H because it's H2 gas. Okay. Then this one, right? So your metal, maybe I can say M, right? Your M, your solid, right? Then this one is going to be M something something plus, right? Equals then plus your hydrogen gas. So essentially, again, right, the anion of the acid is the spectator, right? So this one, right? How do you know which what to put here? Because you see, right, the charge here is charge equals to plus 2. So here it should be 2 plus. That's how charge equals to plus 2, right? So this M is actually a group 2 metal. So this M I deduce that this is a group 2. Okay. Now, what if let's say M is like a group 1 metal, right? So it's going to be so it's actually going to be 2H plus equals plus 2 metal solid, right? It's going to give you 2 metal plus equals then plus your hydrogen gas, right? So this one, right? The high H plus is essentially being reduced, right? So I'm going to draw the arrow here, right? This is 0, this is plus 1. So this is undergo reduction, right? Then this one here, 0 go to plus 1. So this is essentially an oxidation, right? So this is group 2 metal, right? This is group 1 metal. Okay, can? Then the last thing I want to talk about, number 5, halogen displacement. So same thing, you got your F, you got your Cl, you got Br, you got iodine, got astatine whatsoever, right? Wait, is astatine As or At? Let me see. Periodic table. Okay, sorry, At, astatine, right? So you know that this is the most reactive. This reactive. So now, the most reactive, right, is the for halogen is the one that is preferentially reduced because halogen when it gets reduced, it's going by gaining electron, it's going to form a what we call an anion with stable electronic configuration. Okay, so here we go. So reduction, right? More reactive halogen, right? So let's say this one. So let's say Cl minus aqueous, right? Then give you Cl2 chlorine gas maybe, right? Plus this one is so this one should be 2 because there are 2 chlorine, so it's 2E minus. Then oxidation, right? So this one less reactive halogen, right? It's going to be what you call so this one is going to oxidize because the more reactive hydrogen is more preferentially reduced. The less reactive halogen is preferentially oxidized in place. So maybe let's say I do bromine. Okay, so Br2, this one is should be let's say aqueous bromine. Okay, then it's going to give you sorry. Wait, shit, sorry. I got it wrong. Okay, this one is the reduction. So chlorine gas, right, when it reduces by gaining 2 electrons, it's going to give you 2Cl minus, right? So then this one should be A equals. Then this one, okay, this one, right? So this one, it will be like what? Okay, so this one is bromine minus, right? So the Cl2 will displace bromine from from a bromide salt solution, right? So this one is going to be Br2 liquid, right? Should be liquid or can be aqueous also, can be aqueous, right? Then plus 2E minus. So something you will have to remember, right, is that something you will have to remember, right? Is that halogen displacement. Is my pen even working? Halogen displacement. Shit. Okay, so I actually need to write another piece of paper. Okay, so halogen displacement, right, always involve transfer of 2E minus as they are diatomic, as the halogens are diatomic. Okay, so the overall ion equation just balance it. There we go. So this one should be 2, right? So this one is going to be 2Br minus aqueous, right, plus Cl2 gas is going to give you 2Cl minus aqueous, right? Then it displays the bromine out. The chlorine displays bromine out, so it's going to give you plus Br2 aqueous. Right, so this is your ionic equations. Okay, all right. So that's the end of the crash course for ionic equation. Thank you for your attention with Airbus Chemistry and hope to see you again. Thank you.